Hello, my name is Justin Lane. I'm from Michigan State University, and in lieu of giving my physical March meeting talk, I'd like to give a virtual talk on our work integrating superfluids with superconducting qubit systems. And this work was done in collaboration with Murch's group at Washington University in St. Louis. And we have a great paper around this that you can read if you're interested. And so this work was originally slated to be in session B17, which is titled Hybrid Systems, Electro-Optics, Superconductors, and Helium. And so had you gone to this session, you would have heard a lot about superconducting qubits and superfluid helium. And I'm going to talk today about our work putting those two systems together. And so a natural question to ask is, why would we want to do that, right? Why do we want superfluid helium on superconducting qubits? And I can give you two concrete answers. The first one is for thermalization. And that is to say that superconducting qubits are, at the end of the day, solid-state systems. They are coupled to many thermal or possibly athermal baths in the system. For example, we tend to couple our qubits to cavity resonators, and photon bath in this resonator may be much hotter than the base temperature of the dilution refrigerator, and that can lead to dephasing in our qubits. We also know that there is an athermal bath of quasi-particles that exists in the actual superconductor, and when they tunnel across the junction, they can cause depolarization. And liquid helium is a great thermal conductor. It is routinely used actually in the quantum Hall community to cool down the electrons in a two-dimensional electron system to closer to the base temperature of the dilution refrigerator. In addition to thermalization, there's been a recent surge of interest in superfluid optomechanics. So taking optical frequency light and coupling it to the mechanical motion of superfluid. This is this has been pursued mostly because helium is, at the end of the day, a zero viscosity fluid, which means you can make ultra high quality factor mechanical resonators out of it, and people have done this. And if you take the speed of first sound in helium, you divide it by the typical operating frequency of qubits, you get a number or a length scale that is tantalizingly close to what is possible to do in microfabrication. And so one could ask whether or not it's possible to do superfluid quantum acoustics. And I'm going to focus this talk on thermalization, but I want to let that percolate in the back of your head because I'm going to come back to it at the end. So we want to integrate superfluids with superconducting qubit systems. What is the first thing we can do? Well, we can take the simplest qubit system that I know of, which is single junction transmon in the 3D aluminum cavity, and we can pour helium on it. And it's great. And this is actually pretty non-trivial. It's a lot harder than it sounds because helium is a superfluid, which means it has zero viscosity, which means it leaks everywhere. So you need to make every connection in the fridge superfluid leak tight. So here's a picture of our 3D cavity. We had to design these hermetic GPO connectors in order to get helium into or get microwaves into the cell without having helium leak out of the cell. And you also need to fill up the cavity with helium, which we do via this fill line, which is thermally anchored at every stage of the dilution refrigerator in order to not thermally short all the stages, because helium is in fact a good thermal conductor. And if you do this properly, what you can do is you can measure the transmission through the cavity and you see a Lorentzian peak. And as you fill up the cell, you see this peak shift just by virtue of the speed of sound or speed of light in the cell changing as we fill it up with a dielectric. And if you're not careful, your advisor can come into the lab with a rubber mallet and smack the side of the dilution refrigerator, and you can actually see it wobble. But the point is that once we fill up the cell or fill up the cavity with helium, we see a shift in the resonance frequency, but we don't see any systematic change in the electromagnetic quality factor. And this makes sense because helium is a very good dielectric. It has very low loss tangent. And so we can also do two-tone spectroscopy on a qubit, and we in fact see that qubit frequency also shifts. But this one's a little harder to disentangle, right? It's not just the speed of light changing. The capacitive energy of the qubit is going to change by introducing this dielectric. The frequency detuning of the cavity in the qubit is also going to change, as well as the coupling between those two things. And so what we do is we take all of our spectroscopic parameters that we can measure, we fit it to the James Cummings Hamiltonian, in order to extract the values that we cannot directly measure. And so we record these here. We see that EJ doesn't really change, which is what we expect. We see that the capacitive energy goes down by a little bit. It's much smaller than 1 over the dielectric constant, but that's okay because most of the electric field lives in the silicon substrate anyways. And I'll note that this agrees very well with finite element simulations that we did. We see that the cavity qubit coupling actually changes by a little less than what a naive expectation would give. It turns out that if you do a good job at calculating the matrix elements and calculating how the electric field redistributes in the presence of helium, you can get a pretty good number that agrees with this. But yeah, let's get on to coherence properties, which is what we want to study because we want to study thermalization, right? So over the next couple slides, what I'm going to do is I'm going to show you data as a function of temperature. And so each data point that I show you is actually 5 hours of measurements. So you measure for 5 hours, you measure T1 and T2 for 5 hours, and each data point will be the average of those measurements, and the error bars will be the standard deviation of those measurements. So let's start off with depolarization or T1 processes. So we see that the empty circles are when the cavity has no helium in it, when it's a vacuum, and the full circles are when the cavity is full of superfluid helium. Okay, and so what do we see, right? We see that at the lowest temperatures, things don't really change that much. But we get to like around 60 millikelvin, we see that T1 starts to systematically decrease in the presence of superfluid helium. And so this is a little weird. And the hypothesis that we come up with is that as the temperature increases, we might be opening a decay mechanism via phonons in the helium. So what do I mean by that? It is known that you can inject quasi-particles into a superconducting resonator via phonons from some other part of the substrate. And as we increase T1, we decrease the thermal Kapitsa boundary resistance of helium. And so it's possible that phonons in the helium may be able to start exciting quasi-particles in the qubits as we get to these higher temperatures. And if we attribute this shift in T1 to only a shift in the quasi-particle density in the helium, we get a shift of the quasi-particle density of this. And if we should also expect a change in the resonant frequency of the cavity if the quasi-particle density shifts, and you can calculate that it should be around minus 15 kilohertz. And we in fact do see that at these intermediate temperatures, the qubit frequency systematically shifts as a function of temperature around the same value about what we would expect. So we don't consider this smoking gun evidence of this quasi-particle hypothesis, but it does potentially open up an interesting avenue by which we could study quasi-particle phonon interactions. All right, and so talk about dephasing really quick. So we see that at low temperatures, the same scheme here, the empty ones are when there's no helium, and the full ones when the cavity is full of helium. We see that at the lowest temperatures, kind of the opposite thing happens, right? The dephasing time actually systematically increases in the presence of helium. And so we see a temperature profile of dephasing that is qualitatively similar to previous measurements of the dephasing limited by photon shot noise. So if you take a dephasing rate and you convert it to a thermal photon number using the known values of chi and kappa, the cavity line width, and the dispersive shift, you can calculate the effective thermal temperature of the photon path. And we see that when the cavity is empty, we get an effective temperature of about 80 millikelvin, but when the cavity is full of superfluid helium, we get an effective temperature of about 70 millikelvin, which this is kind of consistent that we're able to cool down to around the 60, 70 millikelvin range with the superfluid helium. And for completion, we also measured the excited state population of the qubit, and we don't really see a change in that, but that's once again to be expected because even when the cavity is empty, we seem to be bottoming out around 50 to 60 or 40 to 50 millikelvin, which is roughly a little below what it seems that the superfluid is able to cool down to. Oh, wrong way. And so where do we plan to go with this in the future? It would be nice to really suss out the underlying physical mechanisms of what's causing these changes in coherence properties, right? So what you can imagine doing is we could do power spectral density of the fluctuations with and without helium to see if we can figure something out about these mechanisms. Or we could do a direct measurement of quasi-particle dynamics, which could help this hypothesis of quasi-particle limited T1, and we're actually pursuing that one right now. But I wanted to get back to this idea of superfluid optomechanics or superfluid quantum acoustics, and mention that an increase in period dephasing means that there's little spurious coupling to any mechanical modes in the helium, right? And so one could imagine that we could optimize the geometry of our qubits to strongly couple to one preferred degree of freedom in the helium and not have to deal with the rest of these mechanical motions interacting with our qubit. And so that would be, this is a indication that superfluid optomechanics may be something that, or superfluid quantum acoustics may be something that is a viable path to do. And with that, I would like to acknowledge our team, specifically my PI, Professor Johannes Pollanen. I'd like to thank the NSF and the Jerry Cowan Endowment for funding for this research. And you cannot ask me questions in person, but you may comment on the YouTube video or email me, and I will be happy to respond. And I'd like to thank you for listening.